Welcome students to the lecture series of complex analysis with course code MAT18R4026, Block 2, Unit 2.2, offered by the Department of Mathematics, Karasalingam Academy of Research and Education. In this lecture, I will be covering the Cauchy's theorem over a disk and a rectangle and index of a point with respect to a closed curve. So the Cauchy integral theorem, it's also well known as Cauchy-Gauss theorem in complex analysis, named after this famous mathematician, Augustin Louis Cauchy and Edward Gauss, is an important statement about the integrals for holomorphic or analytic functions. Both are same basically, holomorphic and analytic in the complex plane. Now, Cauchy integral formula, it expresses the fact that a holomorphic function defined on a disk is completely determined by its value on the boundary of the disk. I will be describing the meaning of this while discuss the topic, and it also provides integral formula for all derivatives of a holomorphic function. So from this formula only we will get to know that analytic function is differentiable up to any order. Okay, so if it is differentiable of if analytic function is differentiable of one order, then as you all know, the analytic function means it's differentiable basically. Then up to any order you can take the derivative for any analytic function. This will be assured by the Cauchy integral formula. Okay, so the winding number or winding index of a closed curve, both are same concept only, in a plane around a given point is an integer. It has to be an integer. Okay, represent the total number of times that curve travels around counterclockwise around a point. Okay, suppose there is a fixed point and you are traversing the point counterclockwise, and the number of times you complete full rotation around the point following that path or curve, this is called the winding index of a closed closed curve around that particular point. Okay, so let me move to the second slide. Okay, so this is the Cauchy's integral formula. Okay, so what it says, theorem 4.1. So it says, so let me take a highlighter. Okay, oh, so theorem 4.1. Suppose capital C is a simple closed curve and the function f of z is analytic on a region containing C and its interior. So let me describe it with the help of this image. Okay, so this black curve defined, so this plane, consider it as complex plane, and this black curve, consider it as a curve. It's, as you can see, that it's traversing counterclockwise. Okay, and further you are given with a function f of z which is defined on the region containing C and its interior. So your function f of z is analytic, is defined on a larger domain which contains this curve inside it. Okay, now we assume C is oriented counterclockwise as it is depicted here. Then for any z0 inside C, now z0 be any point inside the region bounded by the curve. Okay, then what it says that f of z equal to 1 by 2 pi I contour integral over the curve C f of z divided by z minus z0 into dz. Okay, so this is the mathematical form of this particular formula, but it says physically something very interesting. So try to understand it. You know the function f of z on this curve only. To perform this integration or contour integral, you need to know f of z on this boundary curve only. Okay, you do not require the you do not require anywhere else. I mean, the functional form of f of z anywhere else apart from this curve. So with the help of this information, I mean the information on the boundary, you can find out the value of this analytic function f of z inside any arbitrary point z dot. So that is the power of this theorem. Okay, the function is not known to you when it was given inside this boundary curve. Only thing you know on the boundary, but with this help of this theorem, you can find out the value of this function inside any arbitrary point z naught. Okay. Okay, it is also written maybe here. So I'm just reading out. Cauchy's integral formula, simple closed curve C, f of z is analytic on and inside C. This is remarkable. It says that knowing the values of f on the boundary curve C means we know everything about f inside. Okay, so it is also written over here. Very important aspect of this. So you would only need to know the functional form of this particular given function f of z on the given contour or on the given curve only. Then only you can say the value of this given analytic function f of z inside the particular region bounded by the curve. Okay, this is probably unlike anything you have encountered with functions of real variable. So we don't know, there is no theorem like this in real analysis. Okay, so it's only complex plane it is possible. Okay, so with a slight change of notation, you can write uh, z as w. We often write the formula this way also. F of z equal to, so f of z is any given point inside the curve here, which is denoted here as by z naught. Simply we write it as z, and this z is can be written as w. So with this simple change, this formula gives the all information of the function inside the region also. So this is a very good example. So compute this integration over C, contour integration over the curve C, and the given integrand is this e to the power z square divided by z minus 2 dz, where C is the curve shown. I mean this curve, and its analytic form is also given. Okay, this curve. Let f of z equal to e to the power z square. F of z is entire function. Obviously, f of z is analytic everywhere on the complex plane. That's why it is also entire function. Since C is a simple closed curve, okay, this is a simple closed curve as you can see, and it also traverses counterclockwise, and z equal to 2 also inside C. Okay, z equal to 2 since here 2. So that's why we are considering the number 2, and we can see that this curve basically includes the point 2 inside. Okay, now so therefore using Cauchy's integral formula, we can definitely write 2 pi I f of t equal to 2 pi I into e to the power 4. Okay, so it's very easy. And another example I want you to consider, do the same. I mean, find the integral where everything is same, but the point is outside of the given curve. Okay, so since the curve, if we consider this integrand e to the power z square divided by z minus 2, and 2 is outside of this region, I mean region bounded by this curve, therefore using Cauchy's formula only, okay, we can say that function is analytic everywhere on the curve and inside the curve. Therefore using simply Cauchy's theorem, we can conclude the integral will be 0. Okay, So Cauchy's integral formula may be used to obtain an expression for the derivative of f of z. Okay, as I was saying, uh, once an analytic function is given to you, that's mean it's differentiable up to any order. So by using Cauchy's integral theorem, one can show that the integral over C or the closed rectifiable curve is equal to the same integral taken over arbitrarily small circle around A. Since f of z is continuous, we can choose a circle small enough on which f of z is arbitrarily close to f of A. So Cauchy's integral formula is worth repeating several times. So now we give for all derivatives fn, if n this will be on suffix. Okay, that means n times derivative of the function f of n defined at z of f. This will include formula for function as special cases where C is a simple closed curve oriented counterclockwise and z inside C and f of w is analytic on inside C. Okay, now we will define Cauchy's Cauchy's integral formula is already defined. Now we will define zeros of analytic functions. So what is it? Let f of z be a function which is analytic in a region D. Let A belongs to D. Then A is said to be a zero of order R for f of z if f of z can be written in this form. What is this? F of z equal to z minus a whole to the power R into phi of z, where phi of z is analytic and at A, phi of A is not equal to 0. Then in this case, we will rather say that A is the zero of the analytic function f of z of order R. So there are some examples of that. Suppose f of z equal to sine of z. Now we know the infinite expansion of the sine z, infinite power series expansion. So this gives as z minus z cube by 3 factorial plus z to the power 5 by 5 factorial minus dot 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 dot. So we can take z outside. Okay, so that gives z into phi of z. So what we note here that phi of z is analytic and phi of 0 is not equal to 0. So therefore 0, I mean the origin is a 0 of this analytic function of order 1. Okay, again we have another example here. So what it says, suppose f of z is given in this form and f of z equal to 0, that's only when the numerator is 0. So which gives z minus 1 into z square plus z plus 1 equal to 0. Now uh, therefore there are zeros of from this two factor, and all of us we know that this is nothing. This equation will nothing but the cube root of unity. Z has to be the cube root of unity. So this is 1 omega and omega square. These are the roots of this equation, which can also be followed here. We can, and I will encourage you to do the calculation. You can find it very easily. So 1 will be given for this factor, and this quadratic factor will give you these two roots. One is omega, another one is omega square. So these are the three zeros of this function, each of order 1. Okay, so there are some more examples. Okay, compute this integral where C is the circle of radius 2 centered at origin. So this is the closed contour, which is again a circle of radius 2 centered at origin. So f of z equal to z minus 2 whole square. So clearly f is holomorphic, okay, everywhere in the interior of C. Okay, this is a simple polynomial. So this is rather a entire function. So analyticity is obvious. Hence, by Cauchy's integral formula, what we can write 2 pi I into f of minus 1, since z plus I can be written as z minus of minus I. So according to the Cauchy's integral formula, we can write it as 2 pi I into f of minus I, where f is defined as this. Now if we put minus I here, and calculate it and simplify this expression, we can easily find out the integral value will ultimately be minus 8 pi plus 6 pi I. This I am leaving up to you. You can check it. Okay. Okay. So similarly, these two examples also I would like to keep it as homework. Okay. You just try to find out the value of this integral using Cauchy's integral formula. And this is very easy. Basically, I can do it. So with this, I stop this lecture and see you all in the next lecture.